Hey, welcome back. This is the last section in Chapter 8, and it's on improper integration. So we'll be able to do some integrals that we might not necessarily be able to do in Calc 1 using limits. Okay, so the first type, there's two types. The first type we'll look at are the infinite interval types. And the big red flag that you'll see is an infinity symbol in one of the limits or both limits. So number 6 will see the infinity symbol in the top of the limit. Okay. And what does this represent? Well, you can think of it visually as representing the area underneath this curve from x equals 2 to infinity. So if you just kept on adding up all of the area underneath that curve forever and ever from 2 to infinity, that's what that integral is supposed to represent. Okay. So the way we're going to approach it is by actually stopping this integral at some variable b, and then we'll get an expression for this blue area here, okay, in terms of b. And then to figure out the integral, we'll just take the limit as b goes to infinity. So first get blue area in terms of b, and then secondly, take the limit as b goes to infinity. Okay, so we're gonna introduce a limit here. So the first step is to kind of drop the bad limit, replace it with some variable, and take the limit as we approach whatever was the issue. So in this case, infinity is the issue, so we take the limit as b goes to infinity, and pretty much leave everything else as is. Okay, I'm going to have to integrate here, so let me go ahead and rewrite 1 over x to the fifth is x to the negative fifth. And then we kind of forget about the limit portion and just integrate this expression, and what will happen is you get that formula for the area in terms of b. Okay? Right, so here we go, integrating. You'll have x to the negative 5 plus 1 is negative 4, divided by negative 4. And we have to evaluate that part from 2 to b. Okay. And still not even thinking about the limit yet. So plugging in b, well, you could make it look a little prettier at first. So this expression will be negative 1 all over 4x to the fourth. Okay. All right, and now we could put the limits into the antiderivative. So the limit as b goes to infinity of negative 1 all over 4b to the fourth minus negative 1 all over 4 times 2 to the fourth. Okay. And once you simplify that, you can take your limit and you'll have your answer, if there is one. So one problem is that these things won't always exist. Okay, they can go to infinity, and in those cases, we'll just say, well, it's divergent. Okay, we'll say the integral is divergent, and you kind of think of that as not adding up to some finite number. So we have negative 1 over 4b to the fourth, and then plus 1 all over 4 times 2 to the fourth, I think that's 64. Okay, and then you can kind of look at these limits individually. This first limit, in your margin, you can kind of, all right, what the heck is the limit as b goes to infinity of negative 1 all over 4b to the fourth? Well, that's going to be L over infinity, which is 0. So this first guy is going to go to 0. The second guy is just a constant, 1 over 64. So you'll have the limit of a constant, which is the constant, 1 over 64. And that's your answer. You'll call this type of integral convergent. So there it is. Okay, so it's either going to be convergent or divergent. You have to show work, though. You can't just flip a coin like on a test and say, oh, it's convergent, and you got a 50. No. You got to show me all the work. Even if it's divergent, you got to show me what it diverges to. So I know in the homework it doesn't always do that, right? So for example, at number 4, it diverges, and they don't give you a space for what it diverges to. No, in my problems, you're going to have to tell me what it diverges to, and I'll show you examples once we come across those. Okay. Let's look at an integral where the limit is on the bottom part. Okay. So number 9 is one example. We have negative infinity to 0 of xe to the negative 7x dx. So the setup is pretty much the same spiel. What makes these problems hard is that they'll start throwing in by parts. You'll have maybe some weird partial fractions and stuff on top of everything else. Anyways, again, the issue here is the infinity symbol. So we take a limit. We're going to replace that infinity symbol with a variable, and then take the limit as that variable approaches this bad place. So then we're left with computing this integral, and you kind of forget about the limit in the meantime and just evaluate that expression to get some expression in terms of b, and then finally take the limit of that, right? Okay, so for this character, we need to do by parts. So I set up my u and my dv. So lineate tells me algebraic before exponential, so I have x, and then here e to the negative 7x dx. Differentiating u will give me 1 dx. Integrating dv will give me negative e to the 7x, negative 7x over 7. And then we can go ahead and put the uv minus integral v du into place. So what do we have? Negative x e to the negative 7x over 7. I have to remind myself to evaluate. Minus negative, so it'll become a plus integral of, we can factor out 1/7, and then we have e to the negative 7x dx. Okay. So I'll have then negative x e to the negative 7x over 7. If I integrate e to the negative 7x, I'll get negative e to the negative 7x over 7 times 1/7 will give me minus e to the negative 7x over 49. And then we have to evaluate this thing from b to 0. Okay, so now I'm going to kind of put back in my symbols. B going to negative infinity, I'll have, let's see, plugging in 0 first. So the first term will just be 0. And then the second term, so it will be 0 minus e to the 0 is 1 all over 49. Minus, now plug in b, so you get negative b e to the negative 7b all over 7. Minus e to the negative 7b all over 49. And then we can simplify and clean it up a little bit and see what we get. So I can limit as b goes to negative infinity of negative 1 over 49, distribute the negative, plus b e to the negative 7b all over 7, plus e to the negative 7b all over 49. Okay. And then what are these types, right? So the first type is just a constant of negative 1 over 49. And then if you plug a sequence of numbers going to negative infinity, what sequence I'm plugging in, like negative 10, negative 100, negative 1,000. If I plug those values into this expression here, where does that expression go? Well, it's going to be, for this, I don't have room in my slot for this thing. Well, I'll try to push it in there. If I plug in negative 10, I'll get negative 10 e to the negative 7 times negative 10, which will be positive 70 all over 7. So that's some big negative number. Here it'll be sort of the same thing, negative 100 times e to the 700 all over 7. So it's huge negative. In other words, that term right there is negative infinity. Right? The third term is going to have a similar behavior, except it's not going to have that negative 10, negative 100 coefficients on the outputs. So in that case, it's just going to be positive infinity. And that's a troublemaker, right? Because that is one of our indeterminate forms, infinity minus infinity. Our solution for dealing with those kind of problems is to combine those into one term. So let's find a common denominator and add them up. So I have to multiply the first guy, top and bottom, by 7. So I end up with 7b e to the negative 7b plus e to the negative 7b all over 49. Okay. It's not entirely clear. I mean, that's still kind of, it's negative infinity plus infinity, but we can factor it. So this one's kind of weird, I admit it. I'm glad I did it. So I could factor out the e to the negative 7b, and then I have 7b plus 1 all over 49. So all you're doing is just keep transforming it until it turns into something you could do L'Hopital's or something that is determinate. It's like a Calc 1 type limit. Okay. Infinity, so we have negative 1 over 49. Make it a little bit more clear, you could rewrite this thing as e to the negative 7b times 7b plus 1 all over 49. Okay. And then kind of reevaluate what kind of limit it is. So the e to the negative 7b, if I'm putting in like b equals negative 10, b equals negative 100, it's going to be e to the 70, e to the 700. So that portion is going to go to positive infinity. That first portion, this part, is going to go to positive infinity. The second part is just the equation of a line. Okay? And it has positive slope. It'll be 1/7 slope. So that thing will also go to infinity. If you remember from my last lecture, I said if you have infinity times infinity, that will just be infinity. So overall, the form is L plus infinity, and that will just equal infinity. If you just tack on this L, the infinity is going to be the dominating factor, and overall, you'll just get infinity. So by the way, L plus infinity is equal to infinity. L minus some infinity is equal to minus infinity. Those are two forms that I didn't mention last time. Okay, so yeah, there it is. It goes to infinity, and this guy would be divergent. Okay, so on my test, you would have to show me all that work. I know in the homework it says, well, it's just divergent, but no, you have to put in the work and show me why. Okay, okie dokie. Let's look at another one that's really, really similar. Number 10, it's just it has that infinite part and the top limit, but it's the same kind of I got to do by parts spiel. Okay, so as usual, you drop the upper limit and just replace it with a variable, and then take the limit as b goes to infinity. And then I am stuck with this integral. Right, and again, I need to do my by parts. So u from Lie is the x, and the dv is e to the negative x over 5 dx. And then du will just be 1 dx. And then v, we'll be a little careful this time, it's negative 5 e to the negative x over 5. If you need to do a u sub to figure it out, do it in your margin. Better safe than sorry. Okay. Now I can go ahead and rewrite my integral. So it's going to be u times v, which is negative 5x e to the negative x over 5, minus the integral of v du, which has a negative in it, so it's going to be plus. I can factor out 5, and then I have the integral of e to the negative x over 5 dx. I'm going to be evaluating here soon. Then let's evaluate the second integral there. So the limit as b goes to infinity of negative 5x e to the negative x over 5 plus, well, it'll turn out to be a minus, right? So I just hit the my microphone button to make sure it's still working. Then I integrate the second guy, so we know the integral is negative 5e to the negative x over 5. There's already a 5 in front of it, so it's going to be negative 25 e to the negative x over 5, and then we have to evaluate this from 0 to b. Okay, so evaluate it. Negative 5b e to the negative b over 5 minus 25e to the negative b over 5 minus, now you plug in a 0, so this will be 0, and then minus 25e to the 0. Okay, these two limits are a little bit different because the b is going to positive infinity and not negative infinity, right? So in the previous problem, if you look, b was always going to negative infinity, so when you're doing if you thought of it in terms of tables, in the exponent you'd have e to the negative 7 times negative 10, which would be positive. In this case, you're going to end up with negative numbers in the exponents. So for instance, just working with that first portion, the limit of negative 5b e to the negative b over 5, as b goes to infinity, if you take a look at your b values, you're going to be getting negative 5. Didn't leave myself enough room as usual. Okay, so let's make a little more room. Negative 5 times 10 times e to the negative 10 over 5, which is negative 2. That equals negative 50 all over e squared. Okay, so that negative in the exponent is actually going to pull that number into the denominator. Let's see what the next guy is. So I have negative 5 times 100, times e to the negative 100 over 5, which I believe is negative 20. So this will be negative 500 all over e to the 20. That e to the 20 is a huge number. I don't even know if my calculator will do it. So the end result is going to be kind of an L over infinity type deal. But in literal terms, as it sits, you have what is technically infinity times 0 form. This portion is going to negative infinity in particular. The second portion is going to 0. So what you need to do in order to evaluate it would be to rewrite it as a fraction. So I'd have negative 5b all over e to the positive b over 5. And then in that form, it's negative infinity over positive infinity. And you could do L'Hopital's. So here I'd have negative 5 in the numerator, and the denominator e to the b over 5 times 1 over 5, which you could rewrite as the limit as b goes to infinity of negative 25 when you do the reciprocal and multiply all over e to the b over 5. And of course that form is L over infinity, which is of course 0. Okay, so that first term is going to shoot off to 0 when all is said and done. The second term, you can kind of see it's in our work that we've already done, oddly enough. Maybe there's some weird pattern going on there. But that will also go to 0. And so you're just going to be left with negative 25, and the limit of a constant is the constant. So you'll get out 25. And so this integral is convergent. Converges to 25. Okay, so those, there's 3 examples. The third example in this category is if you have infinite limits on the top and the bottom. You may be wondering where these kind of problems come up, and I believe they come up in Fourier series. Let's look at Fourier series. Maybe we'll have an example. No, I think those are always negative pi to pi. Well, you could see, no, they're always like negative L to L. But they do come up in probability. So probability integral density, maybe So when you look at these guys over here to the right, you can see they have infinite integrals from negative infinity to infinity. There's a type of job that often sort of recruits math people called being an actuarial, and that's basically kind of a mathy type of actuarial. So I think sorry, it's a mathy type of accountant. Like accountants, I don't think they really do too much calculus, but actuarials will do calculus. And as a matter of fact, to get the job, you got to do you have to take a probability examination in order to move up in rank. Usually they'll have classes that you could take, but a lot of it is these integrals that have infinite bounds on them. And so if you've ever taken like a statistics class, you know, the probability is related to all the area underneath the curve. And if you do all the area underneath the curve, if you integrate it, it's always equal to 1. That's what you're seeing right there in the probability density function definition. But yeah, it's in there. Okay, so it's not just for engineering. There's other applications. Okay, but example 4 is one of those double infinite integrals. Unfortunately, I don't think there was any of these in the homework, which is not a good thing, because if you did become an actuarial, you would be ticked that nobody ever taught you how to do this. So I need to show you this. Okay. And how do I do it? Well, you're going to split it into 2 integrals at a convenient location. So pick 0. And we know from Calc 1 we could do this kind of transformation. And then plus then the other half from 0 to infinity. Okay. And then what I like to do is kind of work with each limit individually. So that first integral, I'm looking at a limit as b goes to negative infinity, going from b to 0 of e to the x all over 1 plus e to the 2x dx. And then I'm going to add that to the other integral, which I'm taking a limit to a different direction, right? So that would be positive infinity, so going from 0 to b of e to the x all over 1 plus e to the 2x dx. The rule is that if either of these integrals ends up diverging, then you're going to say it diverges. So there's no game like, ooh, if it's one is infinite and the other is negative infinite, then we have some work to do. No, it's nothing like that. It's if either part of this integral goes to infinity, you're done. You just stop. And that's kind of why I do it this way. I just want to do one at a time, because if either one is divergent, I'm done. And I don't have to spend my life doing 2 integrals instead of 1, right? Okay. So anyways, what kind of integral is this? You may note, you may not. It's an arctan. You basically have to do a u sub for e to the x, and then du will be e to the x dx, and then dx is du over e to the x. So this dude will be the limit. Whoops, let me go back to black. So this dude turns into the limit as b goes to infinity of the integral of e to the x all over 1 plus u squared times du over e to the x. And of course, that then the e to the x's cancel, and you have an arctan. So arctan of u, back subbing, it'll be e to the x. And then we want to evaluate that from b to 0. Okay, so I have the limit of arctan of e to the 0 is 1 minus arctan of e to the b. Okay, and we're letting b go to negative infinity. Okay, so what the heck was the arctan function? It's the inverse of tangent. Tangent looks like this with asymptotes right here. And that region from negative pi over 2 to the pi over 2, it is 1 to 1. So we can rotate it about the line y equals x in order to get the picture of the arctan function. So arctan looks like this. And it has horizontal asymptotes now at negative pi over 2, and then up here at positive pi over 2. Okay. Okay, so the first part, arctan of 1, that really asks the tan of what angle is equal to 1 in the interval from negative pi over 2 to pi over 2. And so that answer is pi over 4. It's just a constant, right? And then the other guy, what we're doing is putting in b values going to negative infinity. Okay, so negative 10, negative 100, etc. So for us, we'll have an arctan of e to the negative 10, and then arctan of e to the negative 100. That's going to be arctan of 1 all over e to the 10, which is something really, the 1 over e to the 10 is really close to 0. So you're kind of thinking, well, wait a second. Yeah, you're thinking, well, hey, that's going to go to. Seems like I made a mistake somewhere. No, I don't. Maybe I made it in my notes. I think I made a mistake in my notes. It must be my notes. Yeah, so that thing's going to arctan of 0, which is just 0. Okay, so this next guy would be an arctan of 1 over e to 100. Geez, that's ridiculous. So yeah, that's just going to go to 0. So you have pi over 4. So far so good. We have to continue and do the other guy now. So it'd be the integral of, well, we kind of already know how it's going to integrate out. So that's helpful. This will just be the limit then as b goes to infinity of, again, arctan of e to the x. And this time we're going from b to 0. So this will be the limit as b goes to infinity of arctan of 1, which is pi over 4 again, minus arctan of e to the b. Right, so it's kind of the same thing. Arctan, well, the first one's arctan of 0, sorry. Oh, and then this guy should be arctan of 0. So arctan of 0 is just 0. Sorry. So this one's 0. So the second guy, the first guy is going to be 0. That's just a constant. And then this guy is maybe the troublemaker, but you just keep your sentences about you. I'm putting in values like 10 and then 100, etc. So the outputs are going to be arctan of e to the 10. So arctan of something huge. So if you look back up to the picture on the top, arctan of something huge is going to be way out there. And then arctan of something even huger, the b value has gone up. So that's what, did I screw that up? Maybe that's what I screwed up. Let me pause the video. I feel like I screwed something up. Hold on. Oh, I see what I did. I put the stupid limits upside down. I really butchered this one. I apologize. But anyways, the first dude is going to be arctan. So it's 0 to b, not b to 0. Arctan of e to the b, and then minus the arctan of e to the 0, which is 1. That's what I did in the previous one as well. That should be arctan of 1. So this guy here then. Then did I screw this thing up? So hold on. I think we're on target now. The first guy you're putting in 10, 100,000. So this value here is basically going to infinity. Okay, the x value, the input values are going to infinity. So the output value. Again, you look to the picture on the top right, the outputs are getting closer and closer, the y values are getting closer and closer to pi over 2. So that one's going to be pi over 2, and then minus a pi over 4. With the second, with the first integral back to this dude, the arctan of 1 is pi over 4. So I don't know if I butchered that one, but the first sort of integral here that I've done is pi over 4. And then the second one is going to be this pi over 2 minus pi over 4. So if you add pi over 4 plus pi over 2 minus pi over 4, you're just going to get pi over 2 as your solution, or as the representation of the area underneath this curve. Okay. Okay, sorry for butchering that. The example's in the book. If you're super worried, you can just go over to the book and kind of investigate there. But I did sort of drop the ball a bit, so I apologize. There's the picture of it. So it kind of has that normal distribution, that bell-shaped curve like you would see in a statistics class. And that's the kind of application too. It's probability. Okay. There's another application on space orbit. And okay, great. Let's take a look at the other types of integrals now. They're called infinite discontinuity problems. And in my opinion, they're just the same problems tilted 90 degrees. So let's take a look. Infinite discontinuity. So number 15 is a good example. We have the integral from 0 to 1 of 51 over x squared dx. So note, if you have the function f of x equals 51 over x squared, in other words, whatever the heck the integrand is, you cannot put 0 into that function, okay? Because you'd have division by 0, and that's not allowed. All right. So there's a discontinuity at 0, and that's the bottom limit there. And to deal with it, we need to use limits again. Okay, so pictorially, what's going on? Let's take a look at the picture. Okay. So at 0, there's basically just a huge asymptote on this thing. And we are trying to figure out the area going from 1 all the way over here to the side. And so it's kind of, if you just thought of it as being rotated 90 degrees and then flipped, or you can think of the Riemann person going in this direction, it's kind of like the first problem, sort of, you know. It's an infinite amount of area, and this time you're just adding it up as you go up the flagpole. Right? So how do we deal with this? We kind of do the same game. What we're going to do is integrate to some variable. So I'll be integrating this blue region, and I'll get an expression in terms of b, and then I'll take the limit as b goes to the discontinuity. So in this case, I will be taking the limit as b goes to 0 from the right. Okay, so that's another issue here. It's not just a matter of going to positive or negative infinity. You're kind of imagining yourself in this interval, or imagining the Riemann person in there, and they're going to have to push that expression towards the discontinuity. So if you're going to the left, you're coming in from the positive direction. So on your limit, you need to notate this. You're having x going to 0 from the right. Okay, and then you could drop the bad limit, the 0, and then you have 1 up there, and then you have 51. Let's rewrite it, x to the negative 2 dx. And now it's just business as usual. You focus in on this integral, and at the end of the day, you take its limit, right? Okay, so here we go. Whoops, and I shouldn't put x there. We have the variable b. You can use whatever variable you want. It's probably not a good idea to use the same variable you have in your integrand. Okay. Plug in 1, so you get negative 51 over 1. Plug in b, minus minus, plus 51 over b. And then if b is coming in from the right, that's the first limit is just a limit of a constant, but The second limit, you have the limit as b goes to 0 from the right of 51 over b. You know the form is L over 0, so it's either going to be plus or minus infinity. But you could do a little table. So I'm approaching from the right, and then a test value. You know, you have your b, and then your output, just call it y or something. So b here, like 0.1. And then if you plug that in, you get 51 over 0.1. That's a positive over a positive, so this will be positive infinity. So you have some number L plus infinity, and in those cases, that will just equal whatever the infinity is. Okay, so this is positive infinity, and it is divergent. Okay, so those are pretty standard. Let me find a video quiz. So let's give you one of these. It's weird, the homework exercise starts with these, but my notes does not, or something. No, that's not. Hey, there is one of those infinite types. Oh, but they don't have you evaluate it. Okay, so we'll give you number 3 as the quiz. There's the answer is 14, so it's convergent. But that will be the video quiz. One over root x from 0 to 49 dx. So pause, let me pause and figure it out. But that's the video quiz for this section. Okay, so again, the answer is 14. The discontinuity there is at 0, so you're approaching 0 from the right. Let's look at one that's a little bit different. So this is more akin to the double infinity type problems. So I have an integral from -1 to 2 of dx all over x cubed. Okay, so it's the interval from -1 to 2. And this function, one over x cubed, is discontinuous inside that interval, in particular at 0. There will be an asymptote. So in those cases, you need to split the integral at the discontinuity. So you're going to integrate from -1 to 0 of 1 over x cubed dx, which we write that as x to the -3 dx. And then plus this other integral going from 0 to 2. So just like when you have double infinities, you have to split it in the 2 integrals and then evaluate the 2 integrals. Okay. I'll do them both at once. The other time I kind of did two different ones, but well, no, I'll do 2 different ones. We'll see how this goes. So the first integral, I'm on the interval from -1 to 0. And so when you do the limit, you're going to be pushing towards the discontinuity 0 from, this time, the left. Okay, so in that case, you'll have a limit as b goes to 0 from the left of the integral of x to the -3 dx. And then I want to add that to the limit as b goes to 0. And in the other integral, I'm approaching the discontinuity, or I'm taking the limit of the b function as b goes to 0, this time from the positive direction. Okay, so that will be a positive on that integral, and it's the same integral. So this kind of, rather than doing it like the book does it all linearly, putting it one on top of the other, you could use the information from one integral to do the other integral. I think there's a lot of reasons why you'd want to do it this way, but it's up to you. Anyways, this first guy then, x to the -3 plus 1 is -2 all over -2, and then we have to evaluate. Oops, I didn't put the little limits on my integrals. So this is -1 to b, and then this one is b to 2. So you replace the discontinuity limit. Okay. Rewriting x to the -2 over -2, that thing is -1 over 2x squared. Okay? And then putting in our limits, so I have limit as b goes to 0 from the left of negative 1 all over 2 times b squared minus negative, so that'll become plus 1 all over 2 times negative 1 squared. Negative 1 squared, of course, is 1, so it'll just be 1/2. Okay. Then if I put in a 0, that first limit, it looks like it's going to go to infinity, right? So you have the limit as b goes to 0 from the left of negative 1 over 2b squared. And of course, that type is L over 0. And if you're approaching 0 from the left, your input values are going to be values like negative 0.1. So you have negative 1 all over 2 times negative 0.1 squared. And that will be a negative over a positive, so that will be negative infinity. So this first dude is negative infinity, and then the second one is just some number L. So the negative infinity will dominate, and I have negative infinity resulting. And as soon as you either get positive or negative infinity, you're done. Regardless of what the other guy is, it's automatically divergent. And that's just by definition. So you don't even have to do the second part of the integral. No. Okay, good. Number 20 in the homework alludes to Chapter 9, which is the next chapter. And there are some different topics in Chapter 9 that you may not have seen before. You may have, maybe the education system is better than when I went through, but the potential is you have not. And what's going on here is you can kind of decide whether one integral will converge if you know something about another integral converging. Okay, so the implications are given as if this integral, so there has to be two things it holds. First, there's an inequality, right? So suppose f of x is greater than or equal to g of x. Okay? Then if the integral of f of x going from some value a to infinity of dx is convergent, then the integral from a to infinity of g of x dx is also going to be convergent. You may be like, what? Why? Well, think about it visually. Let's say this is f of x. And what we're saying is that we've integrated it and we figured out that all of this area is equal to like 5. Okay? And then consider the curve g of x. Maybe it's definitely less than whatever the heck f of x is, so it's down here. And then if you figure out its area underneath the curve, well, it has to be less than whatever the heck the area is underneath f of x, right? Because g of x is less than f of x, so the area underneath it, you suspect, is also going to be less than the area underneath f of x. And if the area underneath f of x is like 5, you can bet the area underneath g of x is going to be less than 5. Okay? Okay, this also works with divergence. If you have that same inequality, and then note that the kind of the curve on the bottom is divergent. So let's say the curve, the integral of the g of x curve diverges. And you can think of it visually again. That means the area underneath the g of x, that purple area, is like infinity. It forces the area underneath f of x to be infinity as well. Because, and you can just think of it visually, there's more area underneath f of x than there is g of x, and g of x is infinite, so it must mean that f of x is something bigger than that, so we presume it's also infinite. It diverges. Okay? So if the little guy diverges, then the big guy is going to diverge. Okay? So why do we care? Later on, we'll be able to kind of conclude in the we're going to be working with series, and we know from the Riemann sums there's all of these connections between summations and integrals, right? Summation is basically just the limit of this integral. So we'll be working explicitly with the summations. That's this symbol right here, sums of objects. and we will make these relationships between different series to figure out if it converges or not. We're going to be adding up a lot of stuff and seeing if it adds to something, because we'll have kind of a new way of representing the trig functions. Okay, so rather than writing sine of x, it'll turn out we can write sine of x as a sum of a bunch of things. You can think of those things as kind of like little blocks, but you know, it's going to look like this. And so on and so forth. So in order to prove that these things add up to something, we do this work with inequalities, and it's related. You first kind of see it in this integral context. Okay, so we'll get there eventually. But for now, number 20 is kind of what we see as our introduction to this phenomena. And in particular, the problem, let's take a look at part A or part B or something. Let's look at part B, I guess. So we know that 1 all over x to the 6 plus 1, comparing that to x to the 6, how do those compare? Well, I've essentially I've decreased the denominator, therefore I've increased to go from here to here, I decreased the denominator, therefore I've increased the overall expression. So the guy on the right should be greater than the guy on the left. Additionally, then, we can figure out quickly whether or not this integral of 1 over x to the 6 is convergent or divergent, right? So the integral of 1 over x to the 6 dx from 1 to infinity, I think that's or a to infinity or whatever, this thing is going to be a limit as b goes to infinity of the integral from 1 to b of x to the negative 6 dx. And then that will equal the limit as b goes to infinity of x to the negative 5 over negative 5, and then evaluate from 1 to b. Then this will be the limit as b goes to infinity. This thing right here is equal to negative 1 all over 5x to the 5th. So I'll have negative 1 over 5b to the 5th minus plus 1 over 5, and so that will just equal 1/5, so it's convergent. So the inequality plus the convergence of the integral of 1 over 6 to 1 from 1 to infinity implies that the integral of 1 all over x to the 6 plus 1 dx from 1 to infinity converges as well. Okay, so sometimes you won't be able to maybe compute this other integral, right? But if you can establish this inequality, then integrate and determine the convergence of the kind of introduced expression, then you can determine whether the original integral will converge or diverge. Okay? But we're kind of pushing now towards chapter 9. And okay, I'll leave it at that as usual. Thank you for watching. I'll see you next time.